Good morning, Prof Jack Dongarra. Thank you so much for coming down to Singapore and for agreeing to have this interview with us from NTU.
It's my pleasure to be here. Yes, it's always nice to come to Singapore. I enjoy the food and,
Great.
And the people. Yes.
Have you been to the hawker centers?
Not this time. Not this time.
Okay.
Yeah.
Should pencil it in
I
next
see.
time.
Okay.
If I was to introduce Prof Jack, it's probably going to take an hour of this interview, but some of his many notable contributions in computer science has been in the world of high-performance computing. He is the winner of the 2021 Turing Award for pioneering concepts and methods which resulted in world-changing computations, as they put it. He's won the IEEE Sid Fernbach Award, the IEEE Medal of Excellence in Scalable Computing, the Special Interest Group won Supercomputing Award for Career Achievement, the IEEE Charles Babbage Award, the ACM IEEE Ken Kennedy Award, and many more. So I think when we all hear about the ACM Turing Award, right, this is one of the first questions that come to mind is, what were the specific problems that you set out to solve in the early days of your journey that set this in motion?
Right. So I've always been interested in looking at algorithms and seeing how fast the implementation of those algorithms can be on a computer. So I was sort of driven by trying to improve the speed at which those software and algorithms can solve problems. The speed and also accuracy. So those are two things which are critical in terms of doing anything on a computer. We'd like to get the right answer, and we would also like to do it as fast as possible. So starting out, that was my one of my driving points was to develop software that can be used by a wide range of people, and have that software be easy to use, have it be portable, so I could take the software from one environment to another and it still would run, and that the software would be as fast as possible in the environment that it was running in. Those were the goals, I'll say, that we tried to accomplish whenever we put together a software. The kind of software that we're dealing with is software that is used in many fields of science. So it's solving some really basic problems. And that software is also, we call it freely available. So it has a very liberal license associated with it. You can use the software, you can embed it in a product, you could sell that product, and that's fine with us. So the fact that it's freely available, it gets high performance, it gets reasonably good answers, and is available, gives it widespread use in the community. And that community helps develop the software further. So any problems that people have with the software are reported back to us, and we then are in a position perhaps to improve the software in the next release. So there's a interplay that happens with users, with software that has a wide distribution.
I think talking about the software that you've developed, all the linear algebra packages of LinPack, LibPack, Scalable, right? There's so many of this that you've developed and made available, as you mentioned, maybe through the licenses, and now it's formed such an integral part of so many packages that we use, it's part of the R library, it's part of SciPy, which is kind of foundational to most AI computation packages we use. So I want to maybe talk about this in terms of how do you think software engineers can approach open source programming such that it's long-term and sustainable, which we see in the software that you've developed?
Right, so it's not often easy to maintain and sustain software over a long period of time. So the way it works is we get funding. So I'm at a university. We get funding at the university to do research and development, and that funding comes for specific projects. And we do as good as we can on what we propose for those projects. You write a proposal, the proposal gets reviewed, the reviews come back positive, and then you receive funding, hopefully. The problem with software is it after it's developed, it needs to be maintained. It needs to be taken care of. It needs to be continue with the documentation, with the efforts to maintain its integrity, and that is something which is not usually built into the grant when we receive it. So it's something that has to come after, and coming after is not easy in terms of providing the funding for those specific things. So we often have to, I sometimes say we lie, cheat, and steal in order to take care of the software, which is legacy software, which has been developed and still being used and occasionally has to be addressed in terms of making changes to that software. We take resources from other projects and use them to help refresh the software that has been developed and is in use across the community. Because the software is important and it needs to be maintained. It's a failure, I would say, of how software is considered and how it lacks a long-term vision for its care and maintenance.
So do you think the open source can actually make up for this lag? How do you think it contributes?
Right, so open source is a complex word, open source, in the sense that it doesn't really talk about the license or any of the other aspects of it. So you can have open source, meaning the source is available, but there's some restrictions that may be applied to that source in how it's used. If it has commercial use, maybe you have to pay a license fee in order to make that open source used. Our software has no license fee. It's freely available. You can modify our software. You can embed it in products, and you should give us credit for the software, but beyond that, there's no real restrictions on how that software is used. And an example of that is, I'd like to point to MATLAB and Mathematica. Those are packages which have wide use in the scientific area, and they use our software. And that software is used, again, with a very liberal license, so they could sell our software. That software that they sell has a value added over our software. They make it easier to use our software. So I'm happy to pay for a license from MATLAB or Mathematica for the use of my software because they've added value to it, and that value makes it much more easier to arrange.
The open source allows you to do. Have you seen the openness of software kind of change in your time in scientific computing?
Well, so I would say that scientific computing has more of an openness to its software. In the back of my mind, I have this notion that the software was developed using government funding, and because of that, it should be available to people who are in need of that software. So I'm not looking to make money off of the software. I use my software as a calling card for the work that we do. It shows, what we're capable of doing, and the result of having good software and software that we're willing to maintain and take care of over the life of the software is an introduction to what we're capable of doing. And the result of that is usually we're then in a position to get more funds to do other things.
I think that's a great point. Yeah.
We can see that your long-standing focus in terms of this focus on openness and collaboration has played a foundation role in HPC, I guess. And it's very inspiring to see how those principles have stayed relevant through so many waves of technological change. So Professor, looking ahead, how do you see high-performance computing evolving in the next 40 years, let's say? What excites you the most about where the field is heading?
40 years is a long time, so I've been doing this for probably 50 years now, and I've seen many changes take place. And if you were to ask me that question 50 years ago, I would not predict where things are today. So it's very hard, I would say, to read the technology. Things change so rapidly. We've seen the hardware that we use go through various stages and phases, and today, we're at a point where we have microprocessors, which are very powerful. They're put together with graphical processing units to boost the performance. So now we have a device which can run much faster and can hopefully solve problems a lot quicker. When I say put together, I mean we assemble computers today which have millions of processors in them. And we have scientists who try to orchestrate all of that hardware components to bring them to bear on the problems they're solving. So they're really quite amazing computers. It's hard really to know what's going to happen in the next 40 years. But I suspect that we'll see things change in many ways. Today we have CPUs and GPUs. We'll probably have our high-performance computers take on different characteristics so that in addition to the CPUs and GPUs, there'll be other kinds of components that are added to that, where those components can help increase the processing capability, decrease the time to solution for the problem. So those might be in the form of optical computing. So optical computing is where the signals or the data is encoded in light, and we shine that light into a crystal of some kind, and the results of that crystal interaction is to do some operation on the data, maybe multiply those two streams of numbers together. So think about doing that kind of work at the speed of light. That's incredibly powerful, very fast. So that's a potential for the future. Or there's a computing type that's called neuromorphic computing. Neuromorphic is where we have a computer that's trying to imitate how our brains work in terms of the neurons and how those neurons fire and how they influence other parts of the brain. So that's a device. And then we have perhaps quantum computing. So quantum computing today gets a lot of hype. I guess I'm concerned about the hype because the quantum algorithms that we have are there's just a very few of those quantum algorithms. And those algorithms are for very important problems, but they don't extend to the whole range of scientific computing. So, and quantum computing is quite different than our traditional way of doing digital computing. Digital computing, at the end, you get an answer, you get a number out that represents an answer in some sense. With quantum computing, you're going to get a probability distribution that the answer is somewhere in this area, in this region, and you now have a probability distribution that you need to determine. And there's a lot of problems with today's quantum computers being stable. So they're very sensitive. They're very prone to having errors introduced. And until those computers have a better mechanism for correcting faults that occur, errors that occur during its computation, things are not going to progress very far. So, we're waiting, I'm waiting for the time. I think it'll happen. I think there's plenty of room there for research, but the thing that makes me nervous today is we have a lot of companies that are selling quantum computers, and those quantum computers are really not the kind of devices that people will be using in the future. I just don't see it. And there's going to be a lot of disappointment because of the hype and because those machines don't live up to it, where people will be discouraged from using quantum computing. So there's a term that's used, we're going to have a quantum winter, where the people will be discouraged, ignore quantum computing for a while until more research is done and it becomes more attractive for it to be used, and we have a wider set of algorithms and applications that can really benefit from quantum computing. It's a good area for research. I would encourage people to look at it. It's not something that's around the corner. We're not going to have a quantum iPad anytime soon. That may never happen, in fact. But it's a good area because of the potential use is for the problems that it does solve will be remarkable.
I see. It's really a fascinating perspective from your side. And we can see that how the advancement in the scale and complexity really put things into different kind of perspective. And especially with how AI is reshaping the computing landscape right now. And we know that HPC has traditionally emphasized on more high precision, while AI leans towards more low precision and efficiency and speed. So what do you think, how is HPC adapting to this AI-driven trends? And do you foresee convergence or continued divergence between these two fields?
AI needs high-performance computing, something that's very important for driving it. And high-performance computing, the scientific side needs AI. There's a relationship there that there's a need on both sides. We need the speed at which we can do things today with the hardware that we have, the supercomputers that we have. And scientific problems need to take advantage of what AI is capable of doing to help us solve our problems faster. So those are two good things. They're meeting today. They're coming together in a way that's very much reinforcing things. AI is very important not only in the scientific area but all over. I like to think that AI will be more important than the internet is today. So it's going to take on such a role in almost everything that we do. It's going to have an impact on most things that we touch and feel and use and reason about. It's going to play a central role in how things are done. So that's an important aspect, and it needs computing in order to have it take on its capabilities. That brings about some conflicts as well. So AI, in general, needs low precision. So by low precision, I mean they don't need as much accuracy in the results. They just need a few digits to be correct. Scientific computing, on the other hand, needs a lot of digits that are correct. So we have two things which are opposing each other. And today we see that some of the hardware that's being developed is more towards the AI side, more towards having less precision than more precision. NVIDIA, for instance, has some parts, has a new processor. And that new processor is one which has tremendous capability at the low end to satisfy the needs of AI, but it has virtually the same performance at the top end that its previous generation has. So they really didn't invest in doing the high precision hardware. They invested in doing the low precision hardware because of the AI needs. So there's so many more AI applications, and they can sell to so many more people on the AI side than they can on the high performance scientific computing side, that they chose to do an implementation which highlights the low precision operations. So I understand the motivation for it. I feel the scientific people may be in for a surprise and not have high performance computing with a high degree of accuracy be in place for some of the things in the future.
I see. Do you see this might have some effect on the scientific research? Like maybe they do not have enough advancement in terms of the technology compared to the AI.
What we see happening today is people are becoming, let's call it that problem of short precision rather than long precision. Precision which is not as accurate rather than something which is very accurate. It's causing people to become more innovative in what they do in terms of algorithms. So we see creation of algorithms which focus on the low precision and then trying to enhance the accuracy using mathematical techniques to get the same results they would have had they done the whole thing in high precision. That's an interesting aspect. A lot of people are doing work in this area now, and it's something which I think can be beneficial. So it's using both short and long precision. It focuses on the speed at which we can do things with the short precision, and occasionally using the long precision to get the accuracy that's needed in the application. So there's a mixture there, and that mixture is one which I think is a good way forward. It presents some challenges because now we have to rewrite and refactor our software and algorithms to use this different paradigm, but in the end it'll be something which gives us the desired accuracy as well as the performance.
I know you spoke about government funding in the beginning, and now when we talk about NVIDIA and private players entering into research, there's a little bit of bias that gets created into which area receives more funding or more interest of the public, which then fuels the more funding. Do you think this bias is something that kind of fades over a shorter life cycle, or do you think it significantly kind of alters the direction of scientific research?
Well, I think that things get driven in a way that looks at who is using it and how much people can benefit from it. So AI is an example where that's going to get so much attention, so much funding that people are going to be focusing on it. And some of the other things are not going to get the attention or the levels of funding. And that's just part of the way we do things. And what that causes is people to switch the research more towards the AI related things than more traditional. We have a paradigm shift coming, and people have to adapt to it. If you don't adapt, then you're not going to get funded. If you adapt, then you have an opportunity to do these things in the space where AI is highlighted. You could still, the way I think of it is, you still can do what you were intending to do, just recast it in terms of looking at the AI components and aspects of it in a way that makes the results of your research applicable to the AI side as well as to the other side, the traditional side.
That really highlights the tension and the opportunity between these two computing paradigms. I guess the biggest challenge is to balance between these two different perspectives. Also, besides that, you have also spoken about another thing, which is the quantum computing, right? Mentioned just now. Specifically, this potential overlap between quantum computing and AI is very important that in our understanding. So previously in your HPC podcast, you discussed this nexus between AI and quantum computing. Could you maybe slightly elaborate on how do you see this evolving, and whether quantum-inspired numerical methods might play a role in HPC?
So quantum computing is really at its infancy today. It's going to develop over the years. We're going to learn more about quantum computing, quantum algorithms, what the capabilities are, and what the limitations are. But the reality is we have a very small handful of algorithms which can benefit from quantum computing. And those are mainly in cryptography. And we have such a wide breadth of algorithms that we think of for scientific computing. And I don't think quantum is going to address those wide berth of problems. So I don't see quantum helping us with solving partial differential equations. So most of the problems on our supercomputers arise from trying to solve three-dimensional partial differential equations that occur. These occur in many areas of scientific endeavor, and that's really the backbone of how computing is done today, looking at solutions for three-dimensional PDEs. There's plenty of opportunity for AI to help in solving those problems. Numerically, we understand how to do it, and we'd like to do it faster, and that can help. It's like we want to understand the weather tomorrow. So that's a three-dimensional partial differential equation that somebody solves. They do that on a supercomputer today. They look at the forecast. They develop the forecast from that computation, and then it casts everybody. So supercomputing touches everybody through the weather forecast. So that's one way to think of things. AI is helping today. AI can do a good job of predicting what the weather is. You don't have to do this long computation. We could use AI to do the prediction, and people are seeing more and more of that. Quantum, I don't understand how quantum can be used to do the weather prediction. It's just because I don't understand it, and I don't see the algorithms that are there to do it. But maybe in the future, it's something that's an open question. It's a research area, but it's not something which is automatic. So we're going to have to invest, learn, deal with it, become more familiar with the ideas and concepts, develop the hardware to do things correctly. So that's something that's going to take place over the next 20 or 30 years. That's not going to be something that we're going to see tomorrow, quantum computers being used to do weather prediction. I think there's those differences there, and I don't want to have people think that, we're going to have this quantum computer that sits on our desk and does this magic stuff a lot faster than our traditional computers, because that's not going to happen anytime soon. And soon meaning 30 years, 20, 30 years, if then. So there's a lot of things that have to be worked out in order to have that happen. Again, I mentioned this earlier about the hype that has gone into quantum, and it's my feeling that hype is going to lead to a disappointment when they don't deliver on what the claims that are being made, the anticipation of these things. So we have to take that into account as well. So AI is real, it's here, it's being used in our applications. It's something which is making a tangible contribution to scientific work. Quantum is something which is on the horizon and hopefully will emerge at some point as being a useful thing, but it's not today.
Right. So I know you spoke about the quantum winter and the AI winter, and if we're drawing parallels, right, there's a lot of concepts that AI has borrowed from high performance computing and parallel computing and things like speculative decoding. And so we do the same thing with large transformers, and we take a probabilistic inference across models. So in terms of borrowing or building on existing concepts from parallel computing to AI, do you think this is something that researchers or students can actively look at as skill sets or foundational blocks in how they conduct their research, when maybe even in quantum, when they're exploring a completely, I take quantum as an example, but if you're going into a completely new field of research, how easy is it to borrow from these concepts?
Right, so as computer scientists, we have a bunch of tools that we use whenever we tackle a problem. And I'm sure they will have applications. They're already having applications in AI, and they will maybe have applications in the quantum side as well. We think about doing encapsulation so we can get reuse of things. I think of creating a module that can be used to do a specific task, and that module has application in many places. So I get reuse of that, and I think about making that module run very efficiently, and that gets a benefit then across the whole range of things. The software I've been involved with is exactly what this is like. So we develop routines which go into a numerical library. That numerical library is solving specific problems, and those specific problems then are drawn on by various researchers in their work. So we try to design things which have many applications and can be optimized across the hardware platforms. And then people can draw on those components and use them in their application, and hopefully get the performance levels that they hope for on these new machines. I see that as a standard way that we deal with it in computing. That'll carry over to the quantum, and it's certainly in AI today, and will hopefully carry over to quantum computing as well.
Thank you. I think I'll switch gears here to maybe talk about how universities are increasingly recognizing the role of generative AI in students' academic work as a tool in teaching and learning, right? In this, how do you see the industry and research itself shift because of this? Like, for example, what skills do you think students should now prioritize to ensure that they can retain their individuality, or they can still maintain a competitive edge when these high-performance tools are now available to everyone?
So everybody should understand how to use some of the large language models. That's the first thing. What are the right prompts to use to get the answers that you need from these things? And use it every day. I use it all the time. I think of it as a primitive form, a replacement for Google, right? I don't even think about going to Google anymore. I go to, say, ChatGPT and ask the question I would have asked Google, because it provides much more context, images. I think gives me a much more accurate view or picture of what I asked for. But everybody should be doing that. It's just part of the way we should be thinking today. And I use it in my area of research. If I want a summary of a particular thing that's going on, I'll ask it to summarize some papers which illustrate these points and give me the references. So then it summarizes what the papers are, and it gives me the references. If I'm comparing some papers and I want to see which one is better than another, I'll throw it into ChatGPT and ask it to do a comparison based on these things. Let me know how these papers compare, and it'll show me how it compares. It's just a way which is going to save time and energy, and allow me or researchers to become much more productive in terms of how we deal with things. But everybody should be using it. This is a wonderful tool that has tremendous benefits. And people should be understanding, again, what the capabilities are and the limitations as well. Sometimes it doesn't quite get things exactly right, and that's part of the process of learning how to use these tools.
Yes, so I think as part of now what universities have to do is to also educate the public on how to use these tools, right?
Yeah, that's very important.
Now I think that the demand for soft skills would also increase because a lot of your hard skills are being taken care of by these tools. So in terms of the social aspect of research, right, you've been vocal in your career about the mentorship you have received. Can you talk about the role of mentorship and why it's important, both giving it and receiving it?
I guess I've been fortunate, lucky maybe is a better way of saying it, to have very good mentors throughout my career. I've had people who were very patient, who were willing to help and willing to guide me in a certain direction. And I wish that for everybody. I tell my students they should do a number of things in terms of their research. One of the things they need to understand is that it is research, and you should expect to fail. So research is a process, and we don't know the answer when we start doing this thing. And we should, as we encounter issues, we're going to fail, and that's an okay thing. The failure is part of the process. So we need to embrace that and learn from whatever we do and understand why it happened the way it did and move on from that thing. I also tell people they should aim high. That is, they should look at research problems which are difficult and try to tackle those problems, not only go for the low-hanging fruit, not only go for things which are easy to do. Go for things which are create challenges. Through those challenges, you'll try to gain better skills and do things in a better way. You should network with people. So networking is an important aspect of research. Be able to engage other people, tell people about where you are in your work and where you're stuck with your problems. And maybe through that interaction, you can gain insight into the problems that you're trying to solve. People are not going to steal your ideas. They're there to help. And you sort of reinforce whatever they're doing as well in the same process. So I would say those are some things I try to instill in the students that I have. Look at problems that are difficult, expect to fail, and do some networking to get things to go.
Thank you for those wise words.
It's very heartening to hear how those relationships have helped you to shape your path and also how you pass this forward to the students. But today, let's say if you were a PhD student starting out in 2025, we would like to know what areas of study or emerging problem would you focus on, and maybe how do you decide on which topic to work on, whether it's important enough or something like that.
If I'm telling people what area should they go into today, the obvious ones are AI. Go into AI, that's a hot topic, and acquire the skills necessary so that you can use AI and use it in whatever field that you're going to really focus on. If they focus on chemistry, AI is going to play a role in chemistry, and that's a fine way. So they need to understand the basics of AI to apply it to these other domain sciences. High performance computing is something that's going to be around. It's always needed. That's a field or an area which can always use smart people in doing things. I did mention quantum, and I would say that's a research area. So it's not something which we're going to use in the next short period of time. It's a longer term thing, but it's something which needs our attention and have people look at and interact with. So I would say those are the three areas that I would encourage people to invest in and look at for their research interests.
I see. So everything that involves AI.
Everything that involves AI, that's right. High performance computing clearly does, and quantum computing, we'll see where that goes.
I see. That's a valuable advice for today's student, which is navigating a very, very rapidly changing research landscape, I could say. As we close up, maybe let's turn to your current visit here in Singapore, in NTU.
Yeah.
What are your hopes for this appointment and the engagements here? Do you have any message for the NTU research community, especially for the young scholars and faculty?
Well, the message should always be follow your passion. That's one of the things I didn't mention before, but for students, you have to find something that you feel passionate about and want to pursue it. If you think about PhD, the topic that you choose, you're going to be the world's expert on this area. So you should be in a position that you really enjoy working in that area. You don't want to pick a topic that you don't have much interest in, but you should pick something that you want to focus on, you want to develop, you want to understand all the details of in a way that you can really address them in your dissertation. You want to, again, aim high in terms of the problems. Don't pick the low-hanging fruit. You want to do things that are going to have an influence or an impact. I always think that, I was fortunate because of the being in the right place, taking advantage maybe of the opportunities that I had in front of me. Through those things and having good mentors, I was able to do some interesting things in my career. I hope other people have that. It's hard to orchestrate that, or it's hard to give you a blueprint to say these are the things you need to do to get to where I am today. That's something that's hard, So some people come up to me and say, "How can I get a Turing Award?" And so, these are not. There's not a blueprint. There's not a roadmap that I can give you other than work hard, do something in an area that's interesting, discover things that are very important, and maybe good things will happen, but it's not predictable in any sense of the word.
And so most importantly, we need to have our passion, work hard, something good will happen.
Yeah.
Yeah.
If you lack passion, then you might as well go home, because it's not gonna work. You need something that you feel that's so important that you follow it, and aim high again. Network with other people, and expect to fail. That's part of the game.
Yeah. Thank you, Prof. That's a wonderful note to add on. So once again, we sincerely appreciate you for taking the time to share your journey and experience with us, from the evolution of HPC to the exciting intersection between the AI and quantum computing. It's been a privilege for us to hear your perspective in life. So we are especially honored to have you here as the IIS Lee Distinguished Professor at NTU. And we look forward to a conversations and collaboration from your visit this time. Thank you very much.
Thank you so
Thank you,
much.
Prof.
Thank you for your time.